Swayam Prabha. Digital India. Educated India.
What we are looking into is only a reversible cell reaction, and reversible cell reaction is such that at equilibrium there is no current flow. That is how we define the reversible cell. Okay, and when we are talking about galvanic cell is a reversible cell, what we are not talking about is an electrolytic cell, which is not reversible cell. Okay, what is the difference between a galvanic cell and an electrolytic cell? See, both the sides I have, the left hand side is the anode and right hand side is the cathode. Okay, in both the cells we have the left hand side as the anode and the right hand side as the cathode. But you see the changes in the sign. The changes in the sign of the two. This is a galvanic cell and that is the electrolytic cell. What is happening in the galvanic cell? In the galvanic cell is the cell reactions will give you an output of electricity, and as a result of spontaneous reaction occurring in the electrode. You have the reaction occurring in the electrode, which is associated both with the electrolytic as well as galvanic cell. But what you get here is the electricity which is produced because of this reaction. And you remember this sign, which is the sign convention, if you remember, it's very easy to remember, not forget ever. Whenever you have a plus sign associated with any electrode, whenever you have a plus sign associated with any electrode, you always remember the plus sign is the place in which the electrons enter the cell, means from the electrode to the cell. Okay, when you have an electrode from where the electrons are entering the cell, that is the site which electrode you call it positive. And any electrode with a sign negative means from the cell the electron is entering that particular electrode. Okay, so negative sign and positive sign is, if you remember this convention, then you will not forget. And what happens in an electrolytic cell? What is the difference between a galvanic cell and an electrochemical cell, electrolytic cell?
We are supplying electricity in the electrolytic.
We supply, yes. We have an external current source which drives the reaction. Okay, the reaction occurs, cell reaction occurs because since it's a not reversible cell, the reaction is not spontaneous. We need an external source which is going to supply the energy to for the reaction to carry on. External source of current is required. The reaction that occurs by effect of external voltage or passage of supply of some source of voltage, which is greater than the open circuit voltage of the cell. Means if you are whatever circuit you have, the circuit voltage which is associated, if that is supposed to be there, the supplied voltage should be greater than that. Only then the reaction, spontaneous non-spontaneous reaction, which is otherwise, is going to be taking place. So the major difference is the galvanic and electrolytic cell is one is reversible and other is not. Non-reversible means it's not a spontaneous reaction which is taking place in the electrode, and for that to happen, to make it occur, you have to have an external source through which the supply of that external source is going to drive the reaction for the electrode, for reactions that are taking place at the electrode. And what we have, how do we find out the EMF? The electromotive cell, the cell potential is when the open exactly opposite source, whatever source of potential. So if you have an external source of potential, and the EMF generated will be exactly balanced, and you will have no flow of current. The condition of no flow of current is the condition where you determine the EMF of the cell, and that is given by the potential of the right hand side minus the potential of the left hand side at the condition where current flow is 0. So this is how you define the EMF. I'm not going to go into the details of what are the types of electrodes which can be there. I hope you can write down the half cell reactions. I'm not going to go into detail. Just look into this slide if you have forgotten how to write the reaction. The electrochemical series, please look into, I may ask question from here, but I'm not going to deal with this. How to write down the half cell reaction, how to write the Nernst equation, what is the standard hydrogen electrode, why it's taken to be, why it is used. I'm not going to deal with that. I'm leaving that to you. Just recapitulation so that I can, if I ask you small questions, objective questions, you're able to answer. I'm begin from here. I'm talking about electrochemical, the equilibrium electrochemistry, where I am talking about a small amount of charge moving across a potential difference phi. If a charge moves across the potential difference phi, what is the work done? It is the phi into the potential difference. That we define as the electrical work associated with the movement of the charge. So this is what we have done previously. If you remember that PV, the delta G is a measure of the maximum non-PV work, non-PV reversible work. So since we are talking about a system which is reversible, so we are applying electrochemistry to a system which is reversible. Okay, so we are talking about galvanic cell, not electrolytic cell, because electrolytic cells are not reversible or spontaneous cells. We are talking about galvanic cell in which you have spontaneous reaction happening at the electrode. And since these are reversible conditions, that means whatever potential you are generating, if you have an equal value of potential associated with that circuit of same value, they should balance each other and the current should stop flowing. So this is the condition for reversibility. And if it is a reversible condition, then if you remember from our past discussions, the delta G gives free energy at given temperature and pressure is the measure of the maximum non-PV reversible work. So delta G at given temperature and pressure should be equal to, if there is no PV work associated, then it should be the work associated with the electrical work, reversible electrical work. And what is that? We are talking about a small amount of Q charge moving across a potential difference. So that work of potential difference into the charge amount will give you that work, and that work should be equal to the say in delta G at constant temperature and pressure, when there is no mechanical work associated with or any other type of work associated with it, only the transfer of electrons. So this is what the say diagram is going to look like. You have a cell potential E. The potential between the two electrodes, that is the cell potential. Suppose you have mu as a nu delta Z. Delta Z, I've always said, is the number of moles associated, and mu is the stoichiometric coefficient. From your reaction equilibrium conditions, this is what we say. This is the progress of reaction. And this progress of reaction, I can say in terms of the moles of ions that is moving. Okay, so the moles of ions, mu is the stoichiometric coefficient, and delta Z is the amount of reaction which is preceded, and the entire, this is going to be a number, and this is going to be also in terms of moles. So total change in moles of the electron I or ions, whatever, if it is having a charge Zi, gets transferred from one location to the other. Okay, so what do we have? The total charge that can be transferred will be How much charge is Zi? When I'm talking about the electron, what will be the total charge which is going to be transferred, and what is the total number of electrons we are associating with? This is the moles of electron. What is the moles of electron? The stoichiometric coefficient into the number of moles. This entire thing is a say in moles. So this is the number of moles of electron, and with a charge Zi. So I can say Zi, the number of moles of electron, total charge will be how much into the Avogadro number, right?
Yes, ma'am.
Okay. So the if see dj is the extent of reaction, this side is the dj, it is gone from this side. This side is the Gibbs free energy. This we have seen that reaction Gibbs free energy is nothing but the change in G with the progress of reaction at a given temperature and pressure. Or we can write down the delta G is equal to the delta G reaction into the progress of reaction. This we have already seen in the previous reaction equilibrium. And we know that the work done, the maximum work done at a given temperature and pressure is equal to the delta G for that particular reaction, right? So the work done is charge into the potential difference, and the charge is, what is the potential difference we are going to have? We have E is the potential electrode potential, the potential difference between the two electrode, and what is the other things which we have? Total charge into the number of electrons. This is the moles of electron which is transferred. So this into the total electron which is Z is taken as to be 1 minus 1. So we have here into the electrode. So what do I have? I have Z F Na into E becomes F. Okay, Na into E becomes F. Then what do you have? E is there, and Z is delta Z is there. Now I equate the two. I equate the two. What do I get? I equate these two, this W and this. I equate these two. What do I get? The delta G reaction becomes equal to mu F E, when F is the Faraday constant, E is the electrode potential or cell EMF. Yes. Now
Yes,
forget about this. This is only for recapitulation. I'm just going through. What I have a reaction in which I say that this is the side of the reaction which is supposed to be spontaneous. If it is going, we are having delta G negative, then this reaction is supposed to be spontaneous until it reaches the equilibrium where you have the delta G becoming equal to 0. Not the reaction equilibrium, but the delta G of the sorry, delta G, not the standard delta G reaction, but the delta G of the reaction becomes equal to 0. So what happens when you talk about the EMF? Cell EMF is related with the opposite sign. Delta G R is equal to nothing but N. What is this? Number of electron into Faraday into F. So if I have to see the values of G and E, they are going to be opposite. So a reaction is going to be spontaneous only when the cell EMF is going to be greater than 0 and the G is less than 0. Okay. If it is otherwise, if this is greater than 0 and this is less than 0, sorry, this is negative, this is positive, and here it is, this is positive, this is negative, and this becomes negative, then what you have is a reaction which is spontaneous in the reverse direction. So if you have to write down the reaction in the reverse direction, will be one which is going to be spontaneous. I hope I am able to make you understand. So what is the standard gives free standard reaction equilibrium? Mean by the standard gives free standard gives reaction equilibrium. We had taken delta G R naught, and that is where what we had evaluated for a reaction, the delta G reaction becomes equal to 0. So we had equated delta G naught of the reaction equilibrium equal to minus RT ln K or Q, depending on the reaction. This was our equation. Now, what we have here in comparison, you just have a look at this. If you have the previous slide, we have equated the delta G reaction as equal to nu Fe. Okay. If I now substitute the delta G reaction as minus nu Fe equal to the delta G naught of the reaction plus RT ln Q, then if you have a diagram, if you have a equation like this, what can you say? What is delta E naught, the standard cell EMF? If I can write this, this is what I have for any reaction. For any cell reaction or any other reaction, this is the statement I have for delta G reaction, where this is the delta G reaction, standard delta G reaction. And this becomes, Q becomes K when you have reached the equilibrium concentration. Okay. Now what I'm saying, I'm replacing this by what I've got from my electrochemical reaction, where say nu Zi charge is getting transferred across the cell potential, which is the cell potential being E. If that that many moles of electron gets transferred, what will be the associated delta G change, associated work, and that work is being equated to the work which we have, delta G, which we have taken as non expansive reversible work. I replace that here. Then what do I see? If I divide throughout by NF, what do I see? I get an expression which is delta G naught by NF or nu F, the number of electrons. And this we say define as the standard EMF. So you can understand what is the standard EMF related to. Standard EMF of a cell is nothing but the standard reaction gives free energy divided by the number of electrons involved in the reaction and Faraday constant. So it is a manifestation of the delta G naught. The standard EMF of a cell is not coming from the cell itself, but it is actually a measure of the delta G, standard delta G reaction of that particular set of reaction which we are dealing with, divided by N and F. Okay. For a cell at equilibrium, Q equal to K, delta G reaction becomes equal to 0, and E becomes equal to 0. So this becomes equal to 0, and then you can find out what is E naught. So how do you evaluate E naught? Is equating the reaction equilibrium with the electrochemical equilibrium which we are dealing with. Okay. What is going to becoming 0 when at equilibrium? The reaction delta G becomes equal to 0, and hence E becomes equal to 0. This is becoming equal to 0. This Q is becoming equal to K. And that time, what do you have? You have E naught equal to RT by NF ln K. The minus sign is not going to be there, which was initially there for the delta G expression. Okay. So you can find out what is the K, the equilibrium constant. Or you can find out what is going to be the standard EMF of a cell if the equilibrium constant is given to you. Okay, this is something which you need to remember. Okay, this is the summary of whatever we have just now discussed, summarized in one page. This is what we were just now talking about. A cell, it is a repeat of the whatever we have just now discussed. A cell which overall cell reaction hasn't changed in chemical equilibrium, that means a reversible cell, do electrical work as the reaction derives from electrons from the external circuit. So the work is going to be delta G into equal to the delta G reaction, and the work done is nothing but the say number of electrons. Avogadro number of 1 mole of electron means Avogadro number of electron into nu into F. We have taken this, we have derived already this, we have come down to this condition. Now, okay, this is the summary of whatever we have done. I'm not more interested in, please read this. How do you find out the E naught? I'm interested in this part. Suppose you have IH ion in the electrolyte solution and the electrical work associated, an electrolyte solution or electron in the condition, whatever be the condition, I have to define the electrical work. And electrical work I have defined as the charge into the Faraday into the total number of change of the ions into the phi. This is what I have defined from the beginning. This is what I have been defining from the beginning, that I have to know the total number of charge into the Avogadro number of electrons into the electrode the potential difference. So if that is the condition which I have, this E is the potential difference E which we had taken, and this is the total number of moles which is getting changed, and Zi into F. This is what we have just now derived for a expressed for a electrical work done. Electrical work done is the total number of charge into the potential difference. So if I have to measure the total charge change in work, it is the total number of moles, which number of moles of the species which is changing into this gives you the total number of electrons into the Avogadro number F into the potential difference. So work done is the total charge into the potential difference. Total charge is what? This is the total charge and this is the potential difference. Total charge is suppose the charge is Zi, and if it is we are dealing with electron, I'm talking about 1 mole of electron, then this entire thing should be in moles. So 1 mole of electron is equal to Avogadro's number. So this with a negative sign, and total number of change in the number of moles of that ion will what we consider. So if that is the consideration, that is how we find out the delta G or the work done. If it is an open system, that you know delta G is nothing but S delta T plus V dP. Plus, if it's an open system, then you have to take into account the chemical potential of the species into the number of moles of that species, change in number of moles. But what you have in addition is when you have a charged species, then not only the number of moles, but also a term which is supposed to be coming from the electrical work, which is associated with the total number of charge into the potential difference. And the total number of charge into potential difference is this one, right? This is the total number of charge into charge. Z becomes important only when you are having ions. When you have only electrons, when we are talking about only cell reactions, we are not talking about any electrolyte, then this Z becomes 1, and you have this Avogadro number associated with it into the of electrons. So that is why we get the Faraday constant into say DNI. So if I have a charged species, only then I electrolytes in the system, then only I write down Z. Otherwise, if I have only electrons in the system, Z becomes equal to 1. Okay. Because charge associated with that is always 1. So if I have to look into an electrochemical system, Then what do I write? How do I write the electrochemical equilibrium? Is delta G when the change in number of moles into the chemical potential plus the number of moles, change of number of moles into the total charge which is supposed to be associated. What is that? The Z for electrolyte, for electron it is 1, phi into F. Phi is the potential difference and this is the Faraday constant. So this is the additional term which is going to be added. But to take into account the chemical potential and also the charge into separately, it becomes quite difficult. So we introduce a new term which is known as the electrochemical potential. The electrochemical potential is written as the mu Carl. Mu Carl is nothing but the mu I plus Zi Fi. Phi is the potential difference, and F is the Faraday constant. Z is for an electron equal to 1. For other ions, you associate, we can have -1, +1, whatever it is. So if I have electrochemical potential, I have a new term which is defined as mu I Carl. Mu I Carl is mu I, which is without the charge, where potential difference is 0, plus the work done associated with the charge. That is the phi into the charge. Phi into the charge is the additional thing which we have added. If it becomes equal to mu curl becomes equal to mu I when there is no potential difference or there is no electropotential difference associated. So this is the new term we have introduced, the electrochemical potential. What is the condition of electrochemical potential equilibrium? The electrochemical potential equilibrium is the same as the one which we had dealt previously. The chemical potential, the electrochemical potential of the ith species in one of the phase should be equal to the electrochemical potential of that species in another phase. That means this of a species, ith species in phase alpha should be equal to the for the same ith species, the value of mu I plus Zi F phi should be equal to in the other phase. In the two phases, they should be equal. Okay. And what is the condition for reaction equilibrium? Reaction equilibrium, if you had no charges, then we had taken mu I, in mu I summed over all the species of I should be equal to be defined as the Gibbs reaction reaction condition for the Gibbs reaction equilibrium. Sorry, delta G reaction. Delta G reaction. Sorry, what am I saying? Okay, and if I have to find out a delta G reaction for an electrochemical potential, then the delta G reaction for a chemical potential was this summed over becomes equal to 0. Mu I summed over I species becomes equal to 0. But for a electrochemical equilibrium, the new delta G reaction should be defined as mu I, mu curl I into mu I summed over all the species should be equal to 0. These are the two conditions. I just want you to write down that you can be how you can write down these two equations. I don't think I should load you with much how to change this, how to write down these equations. You have to do it yourself. I cannot, I can write down, but if I write down, this doesn't make any difference. You can find out what is the value for equilibrium constant from here, where E equal to 0 for this particular expression. Remember what is the condition for the equilibrium, electrochemical equilibrium. That itself I am going to be more interested whether you know or not. And then what will you write when you're writing down the equilibrium constant? And if you can remember what is going to be delta G by T at constant pressure from the fundamental equations, you can apply that with the delta GR for being equal to minus NFE. If you can do that, measure that, if you can equate the two G's, then what you get is that, and this equation which you have already, you can put it here. This applying these two you can apply delta G equal to minus S, and you can equate the two, and you can get this value, and if you differentiate with respect to T. So if you are delta G with respect to T at constant pressure, so if you differentiate delta G with respect to P at constant pressure, you have this delta G. If it is delta G naught, then it becomes delta G S minus delta S reaction naught. That you can apply, and you can get a variation in temperature. I'm not going to do much. I'm going to leave here. I don't want to explore any further. Please write down these equations. I want you to just be able to write down the electrochemical equilibrium. That's all. It's more than required for me. Okay. Then I think I'll stop here. You can exclude the rest of the portion. I'm not going to go into further. The Phyical I have left. I think it is better left that way.